Let's get started.
Yeah.
Okay. Okay, great. Welcome to the Duke CS and ECE seminar. Today, I'm very honored to introduce you Bhuvana. Bhuvana is assistant professor in the Department of ECE from University of Washington Medicine.
Wisconsin Madison.
Wisconsin Medicine.
The different W.
She obtained her master's degree and PhD from Georgia Tech. She is the recipient of NSF Career Award, and Woman Rising Star Award, and the Granger Faculty Scholar Award. Her research interests are in low-power wireless communication and its challenges in practical deployments. Without further ado, let's welcome Bhuvana.
Thanks, Jen. I think most of our participants are in Zoom, but I think, so if we have questions, I think Dan, you'll let me know if there are questions, right? And we can have conversations. Do feel free to pause me, both in person and in Zoom. We can take questions as we're going through. Hey, Rashid. So like Dan pointed out, my research interests are in low power wireless networks, particularly in the context of scalability in low power wireless networks. My research background is in communication. My grad school, I looked at, and it's still an ongoing research in my lab on biological sensor networks. But most of my lab's focus has been on low power, long range, and large scale wireless networks. And I'll talk about each of these terms. Oh, that's on, yes. Should I do something for it to go away?
Yeah.
Okay. That. Oh, it goes away on its own. Yeah. Yeah. So I'll talk about each of these terminologies and why I think it's important to look at that, or why we think it's important to address each of them in wireless networks today. So the term low power wide area networks, or LPWANs for short, encompasses some of the common themes in IoT networks, common themes being long range communication. Let's take smart agriculture as an example. If we want to deploy sensors in a field and there is a base station that's far away, we want that base station to communicate to as many devices as far away into the field as we can. So it's desirable to have a long range of communication in the last mile. And we would prefer to have long battery life. Think of examples in agriculture or smart cities, where we deploy some sensors. We don't want to keep going back every week or every month to replace their batteries or have a continuous power supply. In applications like agriculture, we may not have continuous power supply for that matter. And a third part is a wide area coverage, which is loosely related to the scalability part of my title, which means we want to cover a wide area, geographical area. In other words, we want to have hundreds of devices deployed in a large area and still support all of them together. And the fourth component, I think that's somewhat obvious to most networking or most deployments for that matter, is to have low cost. So these are sort of shared by a lot of IoT applications, and LPWAN, the term LPWAN has become synonymous to those requirements in the recent past. So going forward, I'll refer to LPWANs as the last mile technology that we are going to look at. And to address the needs of these LPWANs or applications that need LPWAN, a number of commercial solutions have started to come up. NB-IoT, LoRa, Sigfox are some of the popular companies that are out there. For example, NB-IoT and Sigfox are similar to cellular networks in that you have to have a subscription to that company to use their resources, whereas LoRa is similar to Wi-Fi, which means you can buy a LoRa device, deploy it in your home, and get it running. We don't need any subscription for that. But the point is, these are some of the examples. There's tens of companies to address the needs of LPWANs that are out there. So why are so many companies looking at wireless communication? Why is low power related to the communication part? Why are we not looking at the low power needs of the sensors or microcontrollers, everything that comes with that? So to get to that, to answer that question, let's briefly look at what a sensor module in some of these IoT applications look like. We'll have a sensor and the whole module is powered by a battery. Here is a microcontroller which takes the data from the sensor stores it in the memory or not, has an interface to the radio module. And I'm going to show this is the current drawn by the device. These are two different microcontrollers, two different radio modules, off-the-shelf radio modules that we can buy from DigiKey today and start using it. So if you look at the current drawn by, the first number is the active current and the second number is the sleep current of those devices. For the microcontroller, it's in the order of milliamps, less than 5 milliamps for that. Whereas the radio modules are at least tens of milliamps. So there's an order of magnitude, higher current drawn by them. And what is power? Current times voltage. So if we have the same voltage for these two devices, the radio consumes, in this case, about 40 times more power than the microcontroller. And we should thank the silicon industry and circuit design embedded system researchers for giving us microcontrollers and sensors that are as low power as we can see today. So that brings us to the conclusion that radio energy is the bottleneck when it comes to Internet of Things or low power networking. And that's why so many companies are interested in bringing low powered networks to the market, because that's still an open challenge. And not only industry, low power communication has been topic of interest for a while now, even before the practical needs arose. So it can go all the way from batteryless communication. We must be familiar with RFID tags we all use in buildings that are entirely batteryless, but they are very short range communication. We have to go so close to the RFID readers, right? And there are somewhat low power devices like Bluetooth or Bluetooth low energy, Zigbee, that are used by commercial devices, but they still have communication range of less than 100 meters. So Bluetooth, again, as we've all used, we cannot go beyond tens of meters from your Bluetooth transceiver, right? And there is even higher powered wireless devices. For example, Wi-Fi and cellular would fall under that category. They can go to somewhat longer range, between hundreds of meters. So if you go outside your home, you lose your Wi-Fi connectivity. If you go outside your city, you lose cellular connectivity. The companies that we saw in the previous slide, LoRa, NB-IoT, Sigfox, fall under the long range category, just going beyond a kilometer of communication. And in fact, LoRa and Sigfox can reach tens of kilometers of communication in certain network conditions. But the reason I want to show these two axes, which is x-axis range and y-axis power consumption, is they are closely related. If you notice batteryless devices, they cannot go beyond short ranges of communication, right? If we need to go longer and longer ranges, either I have to increase my power, just like the way we speak. If we have to reach longer distances, either I have to speak loudly or I have to speak really slowly. A third factor is I cannot have two people speaking in the same room if I have to reach a long distance. And that's where the size of the bubble comes into picture. The size of the bubble is the number of devices this technology can support concurrently. So RFID is a one-to-one communication. You cannot have two tags talking to an RFID. Whereas Wi-Fi would have maybe few devices, less than 10 or 20. Some Wi-Fi can support 100 devices, maybe in conferences. Cellular supports much larger. LoRa, NB-IoT, and Sigfox are poorer than Wi-Fi and cellular when it comes to number of devices it can support simultaneously. And we'll skip the data rate, the color of the bubble for now. We'll come back to that later. So if you notice the needs that we talked in 3-4 slides before, we would like to have low power, or most LP WANs will need low power, long range, and a larger bubble, right? So this is the need of LP WANs now. And there is a gap here in this state of the art, that we don't have a solution that can reach ranges beyond a kilometer or so, is extremely low power with milliwatts of power, and can support hundreds to thousands of devices. And if you notice the color that I've drawn here, it's on the lower end of the spectrum of data rate. And the reason is we cannot have free lunch. So we have to compromise on something. And if all three of our requirements are satisfied, in theory, we cannot also achieve high data rate. So we have to compromise on data rate of individual nodes to achieve the other three. But we'll see later that it's okay to have low data rate in most of the applications that we are targeting. For example, smart agriculture, we won't be streaming videos from a field, right? Most likely we'll be sending moisture data or carbon dioxide data every 10 minutes or every 30 minutes or so. So the amount of data that we have to send is quite low. And that's what we leverage in achieving scalability in LPWAN. And that's the factor that my group leverages in bringing up new technologies.
Question.
Yeah.
So in terms of absolute throughput, what is the target rate for an IoT deployment, for example, at long range?
So absolute throughput as in one device to one device throughput, right?
Yeah.
So of course, it depends on the application. It can vary anywhere from few bits per second to hundreds of kilobits per second. But I wouldn't imagine it to go beyond hundreds of kilobits per second. The moment we cross that boundary, I wouldn't rate that as IoT network, something that cannot be answered with LPWAN. Okay. So the question was, what would we consider the required data rate for one-to-one link in an IoT network to be called low data rate or high data rate? So I think, like I said, it's about few bits per second, anywhere from few bits to hundreds of kilobits per second. So before I talk about the solution, I also want to give some intuition on how we came to that solution. So again, coming to the core problem of why this trade-off exists. So I want to show some relationship between radio bandwidth. This is the physical radio bandwidth in the megahertz that we can achieve. So I'll talk about the relation between bandwidth, range, energy, and see how they're all related to this bandwidth and how they have contrasting needs related to bandwidth. And that's one of the reasons we cannot achieve all of them together. So if we've seen the movie Finding Nemo, Dory speaks very slowly when she tries to speak to Will, right? So that is an example of us trying to have a longer range of communication when we are trying to use narrow bandwidth. So when we speak really slowly, we're using fewer hertz of bandwidth frequency. And that's a discussion we can have later if anyone is interested. But if we speak really slowly, I'll move one more. We speak really slowly, and bandwidth and data rate for now, let's assume they are directly proportional, and low data rate relates to low bandwidth. Let's take that as assumption, as a fact. If you're interested, we can talk about it later. But if I speak really slowly, or if I send data really slowly, I should be able to reach long range of communication. Contrastly, if I speak really fast, I'll reach shorter ranges. And even with Wi-Fi and cellular, we can see that difference, right? Wi-Fi has shorter range, but it has much faster data rates than cellular, because the bandwidth that's provided for Wi-Fi versus cellular is proportionally different. There are other factors too, but this is one of the factors in Wi-Fi versus cellular. Another relation between bandwidth and the energy consumption is, if I speak really slowly, to say the same message, I have to speak for a longer duration. So the time on air, the time for which I have to send data, that's going to be long. And from our previous discussion on who the bottleneck is, we already saw radio is the bottleneck. So if I have to speak for a long time, my radio is going to be on for a long time. So I end up draining more battery, draining my battery faster than I would otherwise. So if I want to reach long range, I'll have to have low bandwidth. But if I want higher battery life, I would end up going for higher bandwidth, right? And the fourth factor I want to point out is, if I speak really slowly and speak for a longer duration, I'll end up colliding with someone else, because everyone wants to send their message. Everyone is trying to speak at the same time. So the probability of two devices colliding would increase if my bandwidth is low. So these are the factors that we are interested in, right? We want to have high range. We want to have high battery, right? The green ones are our desired properties. Lower collision so that many devices can use the wireless channel at the same time, but they have contrasting relation to bandwidth. So how can we get all three of them together? And before asking how can we get, this is the reason we are not able to get all three of them together. And one of the first efforts from my group was called Y Chronos. It's still Y Chronos. It's an energy efficient modulation that we derive to solve the needs of LP vans that we saw in the state-of-the-art figure to get low power, long range, and large scale deployment. I'll briefly talk about Y Chronos. I won't go into specifics of it, but a conventional modulation is looks something like this. We might have seen in networking courses or any data communication. This figure might look similar, that might look familiar. We have some header, something to say what the message is, and the data that we want to send. So the more data I have to send, the longer is my data packet going to be. So we propose Y Chronos, where we convey information in the time between two short symbols. The time interval between two messages is the message itself. So before texting and calling was free, all minutes were entirely free. We used to have every text and every minute of call count, right? So my friends and I used to have this code that I'll call if it rings 3 times and I call you after 30 seconds. This is what I want you to do. And if I call you and wait for a minute and call you again, you'll have to do something else. So we had a code book of calls and the wait times between the calls, or the number of rings on top of that, to say what we want to convey, because we had limited pocket money and we couldn't spend all of that on our telephone bill. So when we designed that was the example that came to my mind. I wish I came from that example to the solution. Unfortunately, that wasn't the case, but I thought that analogy fit really well in there. So coming back to Y Chronos, the way we are going to send information is we'll send a really short message. And when I say really short, the reason I say really short is that's critical in getting the low energy consumption. So we'll always send, irrespective of the data that we have, we'll always send a preamble. This is for a single transmitter, and a postamble that's unique to that device. And the more data I have to send, the longer is my wait time between them. So looking at the terms that we had before, the time on air and the time for which my radio is on is only the duration of my preamble and postamble. So whatever be my data, I'll always send the same amount of information. So my energy consumption only depends on the length of my preamble and postamble. So if I make it as short as I can, I'm going to save a lot of energy to send data. I'll add one more to this. Too many animations. So if I were to use, say, a conventional modulation, Aloha is a MAC protocol. If someone is not familiar, it's the simplest way for devices to coexist, where nobody cares about anyone else. We just start talking whenever we have data to send. Wi-Fi, on the other hand, uses listen before talk. It listens to everyone. Whereas most IoT devices end up using Aloha because that's the most energy efficient. So if traditional modulation does something like this, 2 senders are using the channel at the same time. Let's say they overlap in their data. Their signals, wireless signals, collide, and the receiver doesn't understand anything. Whereas Y Chronos, because we're not sending any data, most of our information is in the silence period between 2 transmissions. The probability of collision is pretty small because the duration for which I'm on is so small. When I'm actually sending data by being silent between the start and stop messages is an opportunity for other devices to come in and send data. So the preamble and postamble that we saw earlier are messages to indicate my receiver to start and stop counting. So in an ideal world, if I'm the transmitter, I send you a message, you as a receiver, you hear that message, the preamble, and you start your clock counter. And as soon as I send you a stop, you stop your clock counter. And again, in an ideal world, the clock counting between at the transmitter end and at the receiver end would be exactly the same. But of course, that's not true in an ideal world, but we'll come to that in just a second. But from this argument, Y Chronos first saves energy by sending fewer messages through air. It's able to accommodate more and more devices by not sending things through air. How does it improve the range of communication? By sending this short message in the lowest bandwidth that's possible. So if I reduce my bandwidth, remember, we can increase the range. So by reducing my bandwidth of these short messages, I can go to long ranges. And by sending few messages, I'm going to improve my energy efficiency. So these are the, coming back to our requirements, we still use low bandwidth to get long range. But by changing the algorithm, we were able to reduce our time on air solutions and improve battery life. But remember what I told that we're going to compromise on data rate. So if we are going to send information from the example of phone calls, had I called my friend in a minute, I could have conveyed everything I wanted to say. But now I have to have my lookup table and send multiple such calls, wait multiple units of time, and only then can I convey information. So the rate of information transfer or data rate, that's going to be really small, but I can achieve these three factors, which are more important for IoT connectivity or LPWANs than high data rate. So I talked about it in an ideal world, but in practice, of course, timers are not accurate, and there's going to be delays between my transmitter and you receiving data. So there's a lot of timing errors that can happen that would result in bit error. So in that paper in Y Chronos, we solve for timing errors because of which we'll have bit errors. We address that, we add redundancies and error correction codes to solve all of them, and implementing all of that, ultimately we could estimate that we can improve the battery life by 1.5 times compared to some of this existing LPWAN technologies. In fact, these are two different settings. So LoRa at different settings can reach different ranges. So we compared it with different ranges, and Sigfox, which offers the longest range, we can improve by an order of magnitude. And that's a huge plus to Y Chronos when it comes to battery life. And although this was published in 2019, it's our efforts to deploy this in actual fields, that's still ongoing. We have a collaborator in soil science department in Wisconsin who would like to deploy these devices in the field and collect data from their farms throughout the year. So hopefully early fall, we'll have this deployment going on. So it took about 2 years for us to have this engineering effort of making it weatherproof, making everything working with a battery and so on. But really looking forward to having this in the field for a year or so and see what that would look like. So to summarize, we propose Y Chronos to get this low power, long range, large scale network at the cost of reduced data rate. In fact, Y Chronos data rate is much smaller than LoRa and the IoT. It's probably the smallest among all of them, but that's intentional. We want to leverage that and achieve the other three factors. Any questions so far? And I'll take a quick water break in that. In that case, I'll move to the next part of my talk. So I'll get to the previous slide in a second. So this engineering effort to get a paper to product, not a product as in a deployment, it took us about 2 years. So that clearly says it takes so long to get something as simple as Y Chronos, which can be implemented with off-the-shelf devices, which is what we did. The prototyping took us really short time, but make it weatherproof and have it at an elevation in a field and which antenna to use for long-term deployment and so on. Each of those factors matter, and it's hard to make an impact on that in the short term, right? So we also looked at other LPWAN technologies that are out there and see if we can address some of their existing problems. So we looked at LoRa particularly because it's a decentralized network. We can buy LoRa transmitters and receiver and start experimenting on them. We cannot do that with other LPWAN technologies. So the next part of my talk is about addressing LoRa's issues. So if you see LoRa here, it's low power, or it's not high power, at least medium range. It can reach long ranges. The issue comes in the scale of LoRa. So LoRa cannot accommodate hundreds of devices in the same network. So that's where our next target was, to address long range technologies like LoRa and scalability issues in that. So this was a work, it was published in 2021 at SIGCOMM called Concurrent Interference Cancellation. The goal of this work is to decode packets that are colliding. Despite collisions, can we infer all of them? So in addition to LoRa being a decentralized network like Wi-Fi, there's one more reason for LoRa's popularity, which is its physical layer modulation and demodulation. In fact, LoRa stands for long range, and they strive to find a technology that enables long range communication. And that comes from their use of chirp spread spectrum, which is a modulation technique to convey information. And I'll have a crash course on that in the next 5 minutes on how chirp spread spectrum works. I won't go into specifics, but I think knowing that, we can appreciate the challenges in LoRa scalability. So the term chirp itself is not new to us, not in nature. Again, going back to Pixar reference of Finding Dory, the beluga whale in Finding Dory uses a chirp signal to echolocate itself in that movie. I learned about biology through Pixar movies, I think. But chirps are in nature, are used in nature quite a bit. Bats use chirps to locate. We humans have known chirps for over 50, 60 years. We've been using it in radar signal processing to estimate the distance, size of objects, and so on. But LoRa is one of the first companies or first technologies to use chirp spread spectrum to modulate data. So the way chirp works is have frequency modulation to contrast. Frequency modulation conceptually is if I have two different frequencies to transmit, F1 and F2, let's say, I'll send one frequency to send bit 1, another frequency to send bit 2. If I have 16 such frequencies, I can send 4 bits of information in a given unit of time. Whereas chirp says, I'll use the entire range of frequencies that's available to me, and that's how I'll spread information across the frequency. So if I use all frequencies that are available to me to send one data, how will I differentiate between two data symbols, right? And that's where some of chirp's properties come in, which is the starting frequency of a chirp signal. So a chirp's definition is that its frequency increases linearly with time. So if I have two chirp signals that are still increasing, as soon as it maxes, it wraps around and comes back to 0 and goes back. If the starting frequency is different, my receiver can differentiate between these two chirps uniquely. And that's exactly how chirp spread spectrum conveys information. So if it has access to, let's say, 16 starting frequencies, it can send 16 unique chirps and therefore 4 bits of information in a given unit of time. Frequency modulation would also send 4 bits of information, but chirp can reach longer ranges with the same 4 bits of information. Skip this detail for now. And the unique property of chirp is that, again, mathematically we can show, which I'm not going to. If I multiply my chirp signal with a linearly decreasing chirp signal, I'll end up with a constant frequency. So if I transmit a linearly increasing chirp with a starting frequency F1, you as a receiver if you align yourself perfectly with my data and multiply with a linearly decreasing frequency, linearly decreasing chirp rather, you can find out exactly back to your way back to Fi, and you'll map it back to the data you want I set rather. So this process on the right-hand side of de-chirping, this process of de-chirping, that provides a spread spectrum gain or a processing gain, which allows chirps to communicate over long distances. And that gives LoRa an advantage over existing technologies. But that also affects LoRa in that, let me go through this quickly. Let's take two different chirps. So if you see the same chirp signal, if I slide that, I get a different chirp, which means if I'm not perfectly aligned with the symbol at the receiver, I'll be decoding it as a different data altogether. So say on the receiver side, I had two such chirps, and instead of aligning here, I align somewhere. My receiver would think this is the data that I sent. If I align to the second, a few more time samples offset, I think I sent a different data altogether. So although it's simple to improve communication range by using chirps, it also negatively affects LoRa when I'm not perfectly aligned with the symbol. And when single transmitter and a single receiver exists in the network, that alignment is not a problem because LoRa's packet format, the physical header, has sufficient information for us to perfectly align with that symbol. Problem arises, we talked about scalability, right? When multiple devices coexist and multiple packets collide with each other, on the receiver side, after performing de-chirping, it looks something like this, and it doesn't understand who sent what information. So again, in an ideal world, if we are perfectly aligned with the green packet, let's say, I only want to see the green P. But because packets collide and me as a receiver do not know where to start and which symbol I'm looking at, I'll be confused and I'll completely fail in demodulation. So that's where our focus is in concurrent interference cancellation to differentiate between these frequencies and find out exactly who sent what. I'll skip this slide for now, but so let's talk about CIC in the context of an example. Let's take there are three packets that are colliding with each other, and I'm interested in decoding the first packet first. So say it sent a message or a chirp that is C1, and it's colliding with packet 2's message C21, C22, and packet 3's message C31 and 32. And when we perform de-chirping and everything at the receiver, the FFT is going to look something like this, again, for illustration purpose. When I fully aligned with C1 and therefore I see a red, I also see a yellow and a blue corresponding to packet 2, a gray and green corresponding to packet 3. So instead of looking at this entire window, what if I looked at only a portion of that window? I'll still see on my FFT frequency corresponding to C1, C21, and C31. If I look at the second half of that packet, I'll see C1, C22, and C32. So only C1 is common among all three of them, right? And that's exactly what CIC does. We're going to, instead of only looking at one window, we'll look at multiple sub windows and find the intersection of them. And whichever remains after that is going to be the symbol of interest. And we'll repeat this for every packet that we are interested in demodulating. But obviously that's not the end of the story. If it did, it wouldn't be an interesting paper. There is a fundamental challenge to that. We cannot randomly assign such sub windows. We'll not be able to cancel out every other frequency if we randomly choose. I'll skip this slide for that, but the inference of this whole discussion is that Heisenberg's uncertainty principle comes into play in time frequency analysis as well. I can either get good frequency resolution or good time resolution. So when packets collide, If I take too small a window, I'll not be able to cancel frequencies well. If I take too wide a window, I'll not be able to cancel packets in time domain. For CIC, we need, or LoRa demodulation, we need both time and frequency information. So our contribution is in designing interference canceling sub-window subset. That long name is to say the goal is to find the best set of windows to perform FFT on and take intersection. So what are the best windows to select? And here we are going to leverage, or we leveraged rather, the starting the preamble of different packets. LoRa is really good at detecting the start of a packet. So as soon as we detect the start of a packet, we know that at integer multiples of that packet, a symbol exists. So we in CIC know exactly where the packet started, and we'll estimate our windows just like those. We know the boundaries of interfering packets. So we choose our windows to be such that it perfectly aligns with at least one packet. So to cancel packet 2, we'll take windows such that only C21 is present in one window and only C22 is present in one window. Similarly, for the third packet, if we choose a window such that only C31 is present and only C32 is present, if we take the intersection of first two FFTs, we're going to eliminate frequencies corresponding to that packet. And if we take the intersection of these two FFTs, we'll eliminate frequencies corresponding to packet 3, because we divided the window such that in one window, only one frequency exists. And if we do that with the entire window, ultimately our the remaining frequency or the remaining symbol would be C1, which is our interest. And we repeat this for every packet of interest. And we were able to show that we could decode up to 7 colliding packets with the help of CIC. And here's a real trace of a LoRa transmission, and we receive that on a software-defined radio. So if I simply look at the FFT, this is what that looks like. When I apply CIC on that, only the symbol of interest remain. The rest of them are filtered or suppressed. So this is the original. If I simply do FFT on the receiver, I'll see something like this, where I can see peaks all around. In fact, my peak of interest, which is green in color, that's lower than some of the interfering symbols. After CIC, we filtered all of them, and we could see the true peak as the highest one. I'm going to skip this, but the inference here is, again, CIC is not a magic. It cannot continue to cancel every single packet. When two packets are colliding too close to each other, that's still a limitation. So there is a lower bound on how much offset CIC can achieve. And in the paper, we talk about the lower bound, but theoretically, that's not something we're going to look at today. So the limitation of CIC is that when two packets collide too close to each other, we still cannot decode them. But even if we have 7 or 8 packets that are somewhat far apart, we'll be able to decode them. And in addition to the sub-window selection, we had few other modules that had to go into practical deployment, such as different powers of the transmitters had to be filtered out and frequency offset. After incorporating all of that, we implemented CIC on a software-defined radio. We had MATLAB, Python, and GNU radio implementation, and we could leverage LoRa's same pipeline. We reverse engineered LoRa receiver and implemented them all on USRP, and we could get the message out. So a standard LoRa receiver, if we buy a LoRa receiver from the market, whatever be the number of packets we send, in the best case, it can decode one packet, whereas CIC is able to decode multiple colliding packets. And we deployed this in different scenarios, starting with indoor lab space with very high signal to noise ratio, across multiple floors in a lab space, and an outdoor deployment that was about 1.5 by 1 kilometer range. with SNRs as low as minus 15 dB, meaning our signal was 15 dB below the noise floor, and we could still decode that message. So we use standard LoRa modulators, transmitters, and software-defined radio receiver. Jump through the animations to show that on x-axis, we increase the rate at which data was sent, meaning number of packets that were sent across 20 nodes. So we had a total of 20 transmitters. If all 20 of them were transmitting randomly, x-axis is the average number of packets per second in the network, and y-axis was the throughput. The purple line is a standard LoRa, and there are a few other demodulators that have been proposed. Compared to standard LoRa, CIC improves throughput by about 40 times in the higher traffic conditions, whereas in outdoor deployments, it still sees about 10 times improvement in throughput because CIC can decode multiple packets at the same time. So the higher the aggregate rate, more packet collisions occur, and CIC can detect more and more packets from those collisions. Yeah.
In other communication domain, people do wavelength division modulation, right?
Yeah.
Or like CDMA.
Yeah.
In this application scenario, like, did people try this kind of technique, or like why these techniques wasn't work?
Oh, sure. Yeah. So your question is do techniques like CDMA or other methods to accommodate multiple devices to coexist use the same spectrum? Is that used in LoRa? And if not, why is it not, right? So CDMA is another form of spread spectrum, meaning it spreads its information in a wider bandwidth and uses different codes to different users, and that's how we coexist, right? So with LoRa, it still uses spread spectrum, a different type of spread spectrum, chirp. But with chirp, so again, CDMA, the codes are used to uniquely identify different users. And the intent of CDMA was to accommodate multiple users, right? LoRa's goal was to increase the range. They did not start with the design of wanting to accommodate hundreds of devices to coexist. In fact, LoRa's data sheet or their white paper requires devices to send for less than 1% of the time. So it expects devices to send so infrequently that the probability of collision would be low. But they did not expect hundreds and thousands of devices to be deployed because of its popularity. And when those many devices were deployed, they started colliding. So CDMA could be applied on top of LoRa. It would end up draining more battery though, due to its higher spreading factor, and rather because of its use of codes, it would drain more battery, but it's possible to do that. It's just not done because that was not the intent. That's a good question though. Other multiple access techniques on top of LoRa, they've not been applied because we want to go with the simplest one for energy efficiency. That's really the intent. But yeah, in the recent past, some teams have started looking at other medium access control for LoRa. Any other question? I don't see anything in chat either. So that's the end of CIC. I want to talk about, briefly talk about just maybe 2 more slides on our recent work that's to appear in NSDA 2023, where we implemented CIC on top of many other protocols as in a uniform framework, and we've created Docker images of each one of them to be able to implement a CRAN or a cloud access LoRa. And I'll show that in just a second. So if you see here, I'll talk about this in just a second. CIC is one of the many demodulators that have been proposed for LoRa. So it's a hot topic to decode packet collisions of LoRa. And CIC is the most recent one. It has improved over all of them, but we believe there is more to work on that. There was I think 21 census, an ML-based LoRa demodulator was proposed, and there's more work coming up. So we envision all of these demodulators to be something implemented in the cloud and have LoRa gateways replaced by software-defined radios and push the raw samples to the cloud and have multiple demodulators and pick and choose from whichever is essential for that application. And we believe such a cloud-based architecture will fast forward practical uses of research work. But towards achieving that, we need few things, right? We should be able to send data from the gateway to the cloud. We need to compress that data over the channel. And then we need to have a pool of these receivers implemented in the cloud for anyone to use. And in the second half is where our earlier work was published or focused on, where we performed some extensive data collection for multiple scenarios. We performed experiments with varying signal to noise ratio, varying collisions, different interferences, LoRa with Sigfox, LoRa with standard wireless technologies and so on. And all these data sets could be input to any of the demodulators and pass it through LoRa decoder and get the data outside. This was a huge engineering effort because each of the demodulators, research papers that are out there, each one had its own language of implementation. F-Track used MATLAB, CoLoRa used GNU Radio, N-Scale used Python, and so on. So it became a daunting task for LoRa researchers to recreate existing work. So in Open LoRa, we've created this database of, let's just go to that page. I think we can still, oh, we can't see this. Let me share my screen with the entire screen. Oh yeah. So we're continuing some more work to make this easier to access. So we created each of these demodulators in the same with the same programming language, and we've created some Docker container images for each of them so that anyone who'd like to use this demodulator can either use our own data sets or collect their data, just dump it to this demodulator and get the message that we want to receive. So it's a way of comparing existing work, a uniform way of reading all of them in a fair manner or comparing all of them in a fair manner. And to further simplify, we created a Google form where you can either use an existing demodulator or create your own demodulator. Let's say we use existing demodulators. This looks different. I'll just walk through this website for a second. I can, we can then choose which scenario to run. So we have provided links on different scenarios to run and data sets corresponding to each one of them. So users can select which data scenario to run and what all settings to run them on. And we are still camera ready is on the run. We're working to make this as easy to use as we can. That's the ongoing work in my, or recently published work in our group on Open LoRa to standardize existing demodulators. And like I said, our next steps are to put everything in the cloud and address the open challenges in moving LoRa in the cloud. With that, I'll stop my presentation, and I do want to thank those who are in Zoom and in person for staying on a Friday afternoon to listen to this talk. Thanks so much, and I'll be ready and happy to take any questions at the moment.
I have a question.
Yeah.
For this picture. So, when you compress the raw sample,
Yeah.
and send to some data center, the bandwidth you need in terms of the data rate should be much higher than the actual data rate.
Excellent question. Yeah, that, let me repeat that. I love that question because that entire paper is built on that premise, and the question being that. So the question is, if we were to demodulate this data at the gateway, all we'll send to the cloud is bits. And these are messages, short messages. We've already established that. So we may not need a lot of data rate in the backend to store in the cloud. But if we were to push everything to the server, then the backend and the bandwidth needed for that backend is going to be enormous. And in fact, I'll support some of those claims by saying, if a software-defined radio is looking at 1 megahertz worth of bandwidth, it needs a sustained backhaul network layer throughput of approximately 32 Mbps if I don't compress at all. And particularly in outdoor or IoT deployments, when we have these gateways deployed in a field, we cannot expect 32 Mbps sustained bandwidth, right? So that's where the compression comes into picture. So our work, one of the most recent work that's under submission, takes a dynamic compression approach, which constantly looks at BBR, uses BBR to estimate network throughput and constantly adjusts the compression rate to match the backhaul network throughput without compromising the sample's integrity as much as it can. So that's a tough problem, and that's why we're interested in solving that. But we do believe sending everything to the cloud has a lot more advantages than decoding in the gateway. I met someone from Syracuse yesterday at Athena, at Duke, who's deploying these LoRa gateways in Syracuse to read data from the abandoned homes in Syracuse and find out what's happening in those houses. So they mentioned that they could, although LoRa promises long range, in a place with hilly terrain, they cannot go beyond a kilometer. So they needed multiple gateways to cover a relatively short area. So if we push everything to the cloud, we can combine samples from all the gateways and jointly demodulate LoRa data and get a lot more packets correctly than a single gateway could have demodulated on its own. So that's one other example of pushing everything to the cloud, improving throughput. And a third example is the gateway today can receive from one wireless channel, whereas if we push everything to the cloud, this gateway can expand to multiple wireless channels, decode all of them together. So there's a lot of advantages in pushing things to the cloud if we can manage to compress cleverly. But that's an interesting problem, and that's what we're addressing in our next steps. Thanks.
Good. If we have no more questions, and maybe we can.
Yeah, thank you so much again for the opportunity, and stop sharing now. Yeah.